Hey guys, myself Humayun Malik, and our today's lecture is in the continuity of our previous lecture, where we have stated Lioville's theorem and we have also discussed the equation of continuity. And using equation of continuity, we come to know that how to construct an ensemble. So at the end of the previous lecture, we get the relation partial p divided by partial t plus summation, where summation is from I is equal to 1 to 3n into qi dot into partial p divided by partial t plus pi dot into partial p divided by partial pi is equal to 0. And this equation tells us the behavior of the phase point in phase space. Okay, by telling you guys about the phase point, a phase point is the point in phase space and it denotes the system of an ensemble. Okay, this equation also gave us an information that how an ensemble is made. So as we have discussed in our previous lecture that P is the density of phase point and it is denoted by P, where it is the function of Q, P and T. And Q is the position, P is the momentum and T is the time. So we can say that P is equal to P, where P is the function of Q, P and T. So let's name the second equation as equation 2 and the first equation as equation 1. And by differentiating equation 2 on the both on left hand side and on the right hand side with respect to time, we concluded that on the left hand side we simply get dp divided by dt. But on the right hand side, when we differentiate it with respect to time, we get the three partial derivatives. And the first is partial p divided by partial t, where q and p, where q is the position and p is the momentum or constant. Second is partial p divided by partial t, and in this case momentum and time are constant. Third is partial p divided by partial t, and in this case position and time are constant. So by considering partial p divided by partial t, where position and time are constant, and in this case by using chain rule we simply multiply partial qi in the denominator and the numerator, we get the relation partial p divided by partial qi into partial qi divided by partial t, where we know that qi dot is equal to partial qi divided by partial t. So we get the relation partial p divided by partial qi into qi dot. Also considering the second term, which is the partial p divided by partial t, and in this case the momentum and time are constant, and again by using chain rule, in this case we multiply by partial pi in the denominator and the numerator, we get the relation partial pi divided by partial partial p divided by partial pi into pi dot, and in this case pi dot is equal to partial pi divided by partial t. So we can write it as partial p divided by partial t, where position and momentum are constant, plus partial p divided by partial t, where momentum and time are constant, plus partial p divided by partial t, where position and time are constant, is equal to dp divided by dt. And by putting this is in our equation 1, which we have named equation 1, we simply get the partial p divided by partial t plus summation, where summation is from I is equal to 1 to 3n into qi dot plus partial p divided by partial qi plus pi dot into partial p divided by partial pi is equal to dp divided by dt. As our equation 1 is equal to 0, and by putting it is equal to dp divided by dt, we simply get dp divided by dt is equal to 0. Okay, this was our required relation. Now let's discuss what this relation tells us about. This shows that the total rate of change of density, that is dp divided by dt, in the vicinity of any selected phase point of a system as it moves through the gamma space is 0. Sorry, in the as it move in the phase space is 0. And it also tells us that the total derivative of the position with respect to time is also 0. This equation is known as the principle of conservation of density in phase space. Okay, now we are going to state our Lioville's theorem, and it states that the density of state in an ensemble of many identical states with different initial condition is constant along every trajectory in phase space. And finally, we are going to discuss our description. Now we know that the P is the function of position, momentum and time. Now P changes in the volume d gamma, where d gamma is the hypervolume and it is the volume in more than 3 coordinates. So as P changes in the volume d gamma with respect to position, momentum and time, but we can see that the overall P remains constant in the volume d gamma because if some points are leaving the volume due to change in momentum, then at the same point some phase points are entering the volume d gamma due to change in position coordinate. So what we concluded? We conclude that it means that the density of phase point, that is P, along the trajectory of phase point, which is known as the phase line, is constant. So P is constant everywhere. But it doesn't mean that the value of P which is at one place is same at another place. It actually means that the value of P which was at some place will remain same at that place. So this was our lecture in which we have discussed our Lioville's theorem. See you guys in our next lecture. Thank you guys. Allah Hafiz.